Welcome back. Today we're going to learn about our last new kind of stress for this semester, and that is the stress that we find in thin-walled pressure vessels. When you think thin-walled pressure vessels, it could either be cylinders shaped like that, for example, a can of pop, also spheres, maybe a spherical balloon, something that is going to be inflated by pressure on the inside, has a very thin wall. So by thin, we're going to require that the radius divided by the thickness of the wall. So the thickness would be the thickness of the wall right here, or the thickness of the wall right here. The ratio of the overall radius to the thickness needs to be bigger than 10. If it's smaller than 10, then the equations we're going to use here are going to be pretty inaccurate. You really need to come back for an advanced mechanics of materials class to learn how to handle thick-walled pressure vessels. So today we're limiting ourselves to thin-walled pressure vessels, and we are going to figure out what the stress is in those thin walls. So let's start with a cylinder. This could be a pipe, can of soda, anything that is under pressure on the inside and has fairly thin walls. So what we're going to do is try to figure out the stress in a chunk of material that we might cut out. So let's say we wanted to cut out a piece of material right here along the side. We're going to have two normal stresses that will arise. If you think of the interior of the cylinder as being filled up with gas or a liquid under pressure, it tends to want to burst if it's going to fail. So that means that the material in that thin wall is subject to tensile load. So we're going to end up with a tensile stress along the length. We're going to call that sigma with an L. You can think of L for length or L for longitudinal. And we will also have a stress that if you took this out and just cut out this little square, it would be like the up and down stress. But I want you to think of it as it's a stress that kind of wraps around the circle. So if I were to take a cut up here, the stress would act that way. If I took a section of material down here, this stress would come out of the page at us. This is what we call the hoop stress, sigma sub h. So let me write those down. Sigma with the subscript h is going to be what we call hoop stress, and sigma L is what we call our longitudinal stress. Let's do a really quick derivation to figure out what these are going to be equal to. So if you imagine taking a cylinder for a minute and cutting out a chunk of material. So what I'm going to do is I'm going to cut straight down through it with a vertical plane and also chop it off. The piece that I'm cutting out is got a length down the cylinder like that, and it's going to end up being like a half circular shell when I cut it out. And just for fun, because we like calculus, let's make this width be a distance dy. So I'm going to take this little kind of C-shaped chunk of material and I want to rotate it and look at it kind of at a side view. And I'll do the best I can to draw this. This picture never looks as good on paper as I imagine it will in my mind, but rotating and looking at it so what we can see are these two rectangles, which are the actual places where I would have cut through material. So here are the faces where I've cut through material. They're going to have an area to them, and because I've cut straight up and down through them, the stress that acts on those faces will be my hoop stress. So what I have acting outward on this is my hoop stress. It's created by the material that I cut away. So hoop stress acts outward on both of those faces. Here is our distance dy from the picture. What's acting the other direction? We can't just have forces acting to the right. We have to have force acting to the left. What we're going to have is, if we imagine keeping all of the gas or fluid inside of here, the part of it that we cut away is going to be pushing on this big rectangular face with a pressure P. And what I'm going to want is these areas here and here. Well, their length of those areas is going to be dy. How tall are they going to be? Oh, well, that's the thickness of our little thin-walled pressure vessels. So let me draw that as this dimension right here is my thickness. What I want to do is I need a force balance. The force caused by the pressure, P, has got to equal the force from the hoop stress. Because the hoop stress is pointing in one direction, the pressure is pointing in the other. So let's just multiply hoop stress times its area and pressure times its area. Doing that, what do we end up with? I'm going to have the hoop stress, the area it acts over, well, that's going to be dy times t, and there are two of them. I've got the green area up here at the top and the green area down there at the bottom. So that's the right-hand side of my equation. It's the hoop stress times the area it acts over. And then on the left side, I need the force from the pressure. I made that purple. So if the pressure is P, what area does it act over? The width is also dy. And what's the height? It's going to be related to, guess what? The radius of my pressure vessel. From the bottom to the top would be 2 times the radius. And right there, that is the purple area. And this one right here is the green area. I get that my hoop stress is equal to, see the dy's are going to cancel, the 2's are going to cancel. We get PR over T. Very simple equation. And it should make sense that as the pressure goes up, the hoop stress goes up. Units will work out because pressure is going to be units of pascals or psi, and then we've got inches over inch or meters over meter. So units will come out in psi or pascals just fine. So let's talk about sigma longitudinal. And for this one, we want to think about a closed pressure vessel because I just drew a generic cylinder. Sometimes they're closed on the end, like a pressurized cylinder or pressurized can of soda. Sometimes they're open though. Sometimes it's a pipe with fluid flowing through it. I want to focus first on the closed pressure vessel. On the closed pressure vessel, let's again cut it open. Around the outside, I removed part of the pressure vessel, so the part that I removed would be pulling on the other part with a stress equal to sigma longitudinal. And what's counteracting that is the internal pressure. It would have been pushing back with an amount P. And let's do a force balance. We need the force from the pressure to be balanced by the force from the longitudinal stress. Force from the pressure is P over A. Well, this time the area it's acting over is the area of a circle, pi r squared. What about the other side of the equation? The longitudinal stress, multiply that by the area that it acts over. The area it acts over is going to be a thin ring. Now, if this were not a thin wall pressure vessel, you would want to take the area of the outer circle minus the area of the inner circle. We're going to assume that it is so thin compared to the radius that we can just treat this like a uniform strip of material of thickness T that's wrapped around the outer circumference of that circle. So the area of that thin ring is going to be the thickness times, and the circumference of a circle is 2 pi times the radius, or pi times the diameter. So that is the area of the thin ring. Let's solve. The pi's are going to cancel, and one of the radii is going to cancel. And we're going to get that the longitudinal stress in a closed pressure vessel will be PR over 2T. So almost exactly the same as our other equation, except that this one has a 2 in the denominator and this one does not. An open cylinder is also known as a pipe, and in a pipe you've got liquid or gas flowing through it, so we are going to assume that our longitudinal stress is equal to 0. So that's our next equation. If the pipe is open, the longitudinal stress is 0. And then finally for spheres, what's a sphere going to look like? Well, if I take a chunk out of a sphere anywhere, can you see that it basically looks the same in all directions? Well, the way you could derive this is to just take a slice right through the middle of the sphere. And when you take a slice through the middle of a sphere, you would end up with a picture that looks like a half sphere. And what we would have is half of the sphere we've removed is going to pull on the half of the sphere we're drawing with a stress equal to sigma, and the pressure is going to push back the other direction. Which of our derivations does this look like? Does it look more like the hoop stress derivation, where we actually had a rectangle? Or does it look more like our closed pressure vessel picture, where we had the pressure acting over a circle and the longitudinal stress acting around the edges? This is going to look just like our longitudinal. So the stress in a sphere is equal to PR over 2T. It's the same equation as for that longitudinal stress in a closed pipe. And can you see that it wouldn't matter if we cut the sphere vertically like this or horizontally or in any plane? If you cut through the middle of a sphere, you get this exact same picture. So this stress is the same in any direction you could possibly cut open your sphere. Cylinders have 2 different stresses because the derivations give us 2 very different pictures. But a sphere has just the same stress in any direction, and it's the PR over 2T one. Let's do some examples. These examples are pretty fast. We're told it's a spherical tank. We're told the radius. We're told the interior pressure, and we're supposed to find what is the thickness we need to make sure that our stress stays under 12 megapascals. So because it's a sphere, we grab our sphere equation. Stress is PR over 2T. Let's rearrange it to solve for T. T would equal PR over 2 sigma. Plug in some numbers. We have 300 kilopascals. Let's make that times 10 to the third pascals. Our radius is 1.5 meters. 2 goes on the bottom, and our stress, we want it to be 12 megapascals. That's 12 times 10 to the sixth pascals. Now we can cancel the pascals, and our answer will be in meters. Get that that thickness needs to be 0.01875 meters This equation is only valid if our radius is 10 times at least bigger than our thickness. So let's make sure that this is still a valid equation to use. So let's check radius to thickness. Well, our radius was 1.5 meters. Our thickness was 0.01875 meters. We divide those, we get 80, which is definitely bigger than 10. So we are okay. And if you want, you could make that thickness in millimeters. 18.8 millimeters will work. Next, let's do an open-ended pipe. Because it's an open-ended pipe, there will be no stress in this direction. So we will only have a hoop stress. Given a diameter of 4 inches, we are given a thickness of 0.2 inches, and we are given a water pressure in our pipe of 60 psi. They want us to find the stress state. The longitudinal stress is 0 because it's an open pipe. Hoop stress, our equation was PR over T. Pressure was 60 psi. They give us the diameter, so divide the diameter in half, you get 2 inches, and we divide it by the thickness, 0.2 inches. Can you see that this is right on the limit, that 10-to-1 ratio for radius and thickness? We solve that and we end up getting that the hoop stress is 600 psi. They also asked us to find the stress state, which usually means draw a picture. My picture is going to look like is if I took a little chunk of material, really tiny little chunk of material from the side. I have no longitudinal stress this way, but I do have a hoop stress. And that hoop stress is going to be tensile, and we end up with 600 psi. There is the stress state for this open-ended pipe, for a chunk of material on this side of the pipe right here. I want to do one slightly harder problem because these are very simple equations, but they somehow manage to word these so they trick students. So I wanted to do one more example. What we have here is a rigid cylinder that's not going to deform at all. We're going to actually use our thin wall pressure vessel equations to look at this band that's wrapped around the edge. It's an A36 steel band. The 2 inches wide, you don't see any 2 inches on the picture. That is the dimension into the page. It says it's secured around this smooth, rigid cylinder by taking these 2 bolts on the side and tightening them until they have a tension of 400 pounds. So as you tighten this nut and bolt, you will put the bolt in tension, which is going to actually stretch out these bands to make them really nice and tight. What it wants us to do at this point where we got 400 pounds of force in the bolts is to find the normal stress in the band, how much pressure it's going to exert inward on the cylinder, and what's the distance that one of the halves stretches out when you tighten those bolts to 400 pounds. We're actually treating this band like it is a little thin wall cylindrical pressure vessel. We don't really have anything happening longitudinally out of the page, so the stress that's going to occur in here is like a hoop stress. We're going to need a Young's modulus to figure out the length change. So Young's modulus I looked up was 29 times 10 to the 3rd KSI or times 10 to the 6th PSI. And it might help to draw a little picture of what's going on here. What we've got is a little chunk of that material like this, and if we cut it off pretty close, that 400 pounds in that bolt is going to be pulling down on the band. And then that's got to be countered by basically an internal normal force. I'm going to divide that to find the stress, and that's going to be the hoop stress will be that normal force divided by the area it acts over. The normal force is 400 pounds. What area does it act over? That's going to have to do with this area if I cut this open. So the width of it is 1/8 of an inch, and the distance into the page, there's my 2-inch width. So I've got 1/8 of an inch by 2 inches. And we multiply that all out and we get that the normal stress is 1600 psi. And since that is a stress that is tangent to the circle, if you want to think of it that way, we call that our hoop stress. If we think of that little band as being like a thin wall pressure vessel. And that hoop stress has to be balanced out by an outward pressure that the cylinder pushes on it. We can figure out that pressure by using our hoop stress equation. Hoop stress is PR over T. Let's rearrange solving for P. P would be our hoop stress times our thickness divided by the radius. So that's going to be 1600 psi. The thickness is 1/8 of an inch. And then what was the radius? Oh, that's given in the picture. The radius is 8 inches. So we divide by 8 inches. Inches cancel and we get a pretty small pressure, 25 psi. Cylinder is pushing out on the hoop with this much pressure. The hoop is pushing in on the cylinder with that much pressure. It may not have looked like a thin wall pressure vessel situation, but because this band goes around a big radius of 8 inches with a thickness that's much smaller of 1/8 of an inch, that stress around the circumference, which we call hoop stress, has to be related to the actual pressure that gets built up at that interface. Last part of the question, we're supposed to find the distance half the band stretches. So the idea would be that this band would have been a little bit shorter, but because you're pulling both sides with a big 400-pound force, it's going to stretch out. We're going to treat this, even though it's curved around here, like it's more or less straight. And so what we're trying to do is figure out what is the little length change of what's effectively a long strip of material. So you guys remember that equation from a while back in the semester? We're going to use our deflection equation. It's the force times the length over the area times the Young's modulus. We already found the force over the area right up here. That's our hoop stress times the length that we're interested in divided by Young's modulus. Hoop stress we know, that's 1600 psi. Modulus we know, that's 29 times 10 to the 6th psi. We don't know is the length of this. You guys know the circumference of a circle is pi times the diameter. The circumference of half a circle would be pi times the radius. Again here, pi times the radius, which is 8 inches. This is the circumference of the half circle. This comes out to be 1.387 times 10 to the minus third inches. You could write it as 0.00139 inches would be rounded to 3 significant figures. And we solved the problem. There's several problems in the textbook that have these like bands or rings around things. And I want you to think of the band itself as being the cylindrical pressure vessel. It may not seem like it. It doesn't seem very vessel-like to me either. But what this equation does is it relates stress around a circle to the pressure on the inner surface of that circle. And then if it asks you something about length change, or how much does it stretch out, we're going to go back and use our regular old axial deflection equation, which seems a little bit shady maybe because this was designed for things that were long and slender and straight. But once we start using this thin wall assumption, the idea is that this thickness is so small that locally we are basically treating little local chunks of this as though they are straight. So you might end up all the way around the circle by the end, but we're assuming that that curvature is really very small. And so we're going ahead and using our regular axial deflection equation. That's it for thin-walled pressure vessels. Thanks for watching. We'll see you next time.